Welcome to the fifth video of the first series. We're going to discuss the forces that govern biomolecular structure and function. And we're going to begin with a very simple reintroduction to some thermodynamic concepts that should be familiar to us all. First of all, of course, we don't really care so much about the first law of thermodynamics, but we think that the energy of the universe is a constant. What's really going to be interesting for us, though, is the second law of thermodynamics, that disorder or entropy is always increasing. Keep that in your head for a minute, remembering that it'll turn out that the number of degrees of freedom in a system, or the amount of disorder in a system, can determine whether or not a chemical reaction will proceed. We'll also think a lot about the Gibbs free energy of chemical reactions, which just describes an energy flux, whether a reaction is endothermic or exothermic, whether energy is released or required for the reaction to proceed, and we'll generally think about it in these terms. Here's an enthalpic term, and I'll describe that again in a minute, and here's an entropic term, and we'll see that not only the entropy, but also the temperature dependence of that entropy will be critical for determining the spontaneity of our chemical reaction. So that spontaneity, once again, whether a reaction proceeds or not, will depend on the Gibbs free energy. Delta G greater than 0 tells us that the reaction is unfavorable. Positive free energies are unfavorable, and that the reverse reaction instead is the spontaneous reaction. At delta G of 0, the system is at equilibrium. There's no chemical flux. And for negative free energies, the reaction is favorable and spontaneous. Those are sort of definitions. More definitions. Enthalpy. The change in enthalpy, delta H, or heat of a chemical reaction, is a measure of what kinds of bonds are formed or broken. And these can be covalent or non-covalent. Both of those are going to play important roles in driving chemical reactions. Spontaneous processes generally are going to require a negative delta H. Although, again, it's the balance of enthalpy and entropy that determine the overall the spontaneity of the reaction. Entropy is a measure, again, of the number of degrees of freedom available to the system. Another way to say that is the amount of disorder in the system. And spontaneous processes require an increase in the entropy. Right, so we measure free energies in chemical reactions, and this is some of the equations that we use to make those measurements. First of all, we can just write a very simple equation down. A plus B goes to C plus D, and of course these are just coefficients that tell us the relative quantities of those. Those can play a role in subsequent calculations, but for now let's just consider them all to be 1. We can write the free energy of a reaction this way. The delta G equals the standard free energy, and the standard free energy is simply the free energy at standard conditions, 25 degrees, 1 atmosphere, 1 molar each of reactants and products. This may not be a very physiologically relevant set of conditions, but this is our standard state that we consider everything with reference to. We can consider the standard free energy, delta G naught, to be more or less unique for a particular kind of chemical reaction. But the actual conditions in vivo define whether or not the reaction is spontaneous or not. So the delta G becomes more important when we're considering what's actually happening in vivo, and that's because these relative concentrations of the reactants and products determine the overall delta G of the reaction. Now, something fun that we can do is set delta G to 0. That's a sort of a definition of equilibrium, and then we can rewrite the equation in this familiar way. Delta G naught equals minus RT log K, and then the K tells us whether or not the reaction is spontaneous. So now, instead of just thinking about whether the energy is positive or negative, now we're thinking about what predominates, reactants or products. If the K is greater than 1, then we're going to have a spontaneous reaction, and you can think about that yourself, right? The log of a number greater than 1 multiplied by minus a negative integer is going to give us a negative free energy. That's a spontaneous reaction, whereas the log of a number smaller than 1 is going to give us a negative number multiplied by a negative is a positive, so that is going to be a positive delta G, not spontaneous. In any case, what I want you to be able to think about is what the magnitude of the equilibrium constant tells you about whether reactants or products are dominating the chemical reaction, and thus the spontaneity of the reaction. Moving on from that review, let's look at some of those forces now that are governing interactions in biochemistry and biomolecules. First of all, I just want to break it down between covalent and non-covalent interactions, and here we can see the relative magnitude of those energies. Covalent bonds being on the order of 100 kilocalories per mole. We got triple bonds stronger than double bonds, and other kinds of single bonds being of varying strengths, but still on the order of 100 kilocalories per mole. The main thing to note being that the covalent bonds are much, much stronger, on the order of a factor of 10 or more, stronger than non-covalent interactions that actually drive a lot of the structure formation. Now, most of the time we'll be talking about electrostatic interactions, charge-charge interactions, right? Ionic interactions, dipoles, induced dipoles, and everything in between, on down to hydrogen bonds probably being the weakest of those interactions. So ionic interactions being among the strongest, hydrogen bonds being among the weaker of the non-covalent interactions. But we'll see that all of these, weak though they be, drive the formation of biomolecular structure. Okay, so let's think a little bit more about some of these interactions. Van der Waals interaction, which really in itself we can think of as a kind of electrostatic interaction. As an aside, we'll just say that one model of Van der Waals interactions is just the favorable energy of association of two atoms arising from the fluctuating electron density around the atom. So the fact that the electron density is not uniform instantaneously means that there might be partial negative charge on one part of the molecule. That induces a partial negative charge, or a partial negative charge on one atom, even though it's transient, might induce a partial positive charge on a neighboring atom. That's a favorable interaction. So that's how we can break down a Van der Waals interaction into an electrostatic interaction. This is a free energy diagram, and I really like to draw these kinds of curves. They allow us to think about some of the mathematical formulations of these interactions a little bit more simply. What we can see is that there's an energy on this axis, interatomic distance along the x-axis, and let's consider this line to be 0. At long distances, neither of these spheres can sense each other at all. There's 0 energy, either repulsive or attractive. As they come closer and closer together, they begin to feel that favorable Van der Waals interaction, effectively an electrostatic interaction, and that reaches some minimum, right? And that's the Van der Waals contact distance. And beyond that minimum, the electron shells begin to interpenetrate, and that's an unfavorable interaction. So we have a positive energy that shoots right through the roof that effectively prevents those two atoms from interpenetrating. Something we'll spend a lot of time doing is writing down these interactions as mathematical expressions so we can think about what's happening in a Van der Waals contact as well. We would say that as the two spheres move closer and closer together, they begin to experience a favorable negative free energy interaction, and that's a 1 over r to the 6th interaction. That is to say, the distance dependence of that goes as 1 over r to the 6th, the separation of those two atoms. And there's some minimum distance at which we achieve a contact. And then as we interpenetrate, we go through to a distance dependence of 1 over r to the 12th. That is to say, positive free energy, and as those shells overlap, we experience a repulsion. So there's an attractive force and a repulsive force in a Van der Waals type interaction. What I want to really emphasize here is that the magnitude of that curvature, right, the distance dependence of that interaction, whether attractive or repulsive, depends on the size of that exponent. So the favorable interaction occurs over a much longer range. Even though it might be a shallower curve, that also means that that interaction is occurring over a longer range than the r to the 12th repulsive interaction. That's something we want to keep in mind as we think about the relative strengths or distance dependencies of different kinds of intermolecular interactions. Let's move on to think more about electrostatic interactions. Something maybe more familiarly electrostatic would be a charge-charge interaction. So here's a positive and negative charge separated by some distance r, and we can write down a mathematical expression that describes the behavior of those two particles as an energy or a force, and we'll just say that that's the charge on the two particles multiplied together divided by r squared. So that's a 1 over r squared distance dependence, even longer range than the 1 over r to the 6th dependence that we saw for the van der Waals interaction. So very strong, long range interaction. Something else that's useful here in terms of constructing our mathematical expression is that we introduce a Boltzmann constant K, which gives us energy units, joules per degree Kelvin. I should point out that although the Boltzmann constant is typically written in joules per degree Kelvin, most of the time in biochemistry we refer to kilocalories, not kilojoules. As well, it's worth pointing out that this force or this energy also depends on the dielectric constant of the environment, which we won't go into right now. We'll just assume a constant dielectric for the time being. So again, I'm just pointing out to you that we can write down a very simple mathematical expression to describe a phenomenon, which is the interaction of oppositely charged particles. Worth pointing out, of course, that if these were two like charged particles, then we would wind up with a positive energy and an unfavorable interaction or a repulsive interaction as opposed to an attractive interaction. Let's move on to hydrogen bonds, which I suggested might be one of the weaker of the electrostatic interaction, or the electrostatic non-covalent interactions, but an extremely important kind of interaction, as we've already seen in the structure of the DNA double helix. Again, what we have is a hydrogen bond donor and a hydrogen bond acceptor. Partially negative electron pair, electronegative atom bound more or less tightly to its proton. And what I'm trying to show with this sort of cone is the idea that this does not need to be a perfectly linear system. We can deviate around some cone to find our hydrogen bond. So we have some flexibility there, and of course the strength of that bond will depend on how linear the system is. But another way to think about the strength of the bond is to think about the length of the hydrogen bond, and we can look at several different hydrogen bonding systems, realizing that in the first place we can have a variety of donors, and most of the time it's either going to be an oxygen or a nitrogen donating the proton, and a variety of acceptors. Here's a hydroxyl, here's a carbonyl, etc. And sometimes we'll have a sulfur giving the lone pair to the hydrogen bond. And we'll see that different partners give rise to different strengths. In this case, the shorter the distance between the partners, indicated by these arrows here, the stronger the hydrogen bond interaction. So there's a lot of things that govern hydrogen bond strength, including the angle of the bond as well as the partners engaged in it. But again, critical for you to realize that we can form hydrogen bonds with a variety of partners, and we'll see all of those in upcoming lectures. Let's think a little bit about water. As we begin to understand how proteins fold up, it'll be very critical to us that proteins exist in a water environment. Water ultimately is going to define the structure of proteins and other biological molecules, and hydrogen bonding, of course, is very important. Water has multiple hydrogen bonds that it can form. It can donate 2 hydrogen bonds, and it has 2 lone pairs with which it can accept hydrogen bonds. This extent of hydrogen bonding is important for the structure of water. It forms a well-ordered structure, most water molecules striving to satisfy all of those hydrogen bonds, but it's a dynamic structure. Unless we form ice, for example, those hydrogen bonds are labile, they break and form quite rapidly, and so we say that there's a dynamic structure to water. Nevertheless, that structure does seem to be governed by the formation and breaking of hydrogen bonds. And we can get the sense of what the distance between the 2 partners of that hydrogen bond are here. Okay, now entropy comes into play when we think about how the structure of water actually drives the formation of protein structures. So, natural forces and interactions in biochemistry, hydrogen bonding, and the hydrophobic effect. I think we're familiar with the notion of the hydrophobic effect, and we want to be careful to distinguish the hydrophobic effect from an actual physical force. Instead, we like to think that the hydrophobic effect is in fact an entropic effect. The entropic effect arising from the entropic cost of ordering water molecules around an exposed hydrophobic surface area. So what I've drawn here in this cartoon are you could imagine that these little, they look like little flower shapes, are actually phenyl rings or benzene rings, nonpolar structures. And in this case, those nonpolar structures are interacting with each other through van der Waals contacts, a favorable interaction. In this case, what we've done is expose a nonpolar surface area to water. That nonpolar structure, completely unable to form any satisfying hydrogen bonds with the water environment, and so what the water molecules are forced to do is to form a clathrate or cage of more or less static hydrogen bonds around that structure. That reduces the number of degrees of freedom available to the system. The water is no longer dynamic, but it's well ordered. That's an entropic cost. So we think that in order to avoid the entropic cost of exposure, we bury. So the hydrophobic effect is essentially oily surfaces interacting with each other, hydrophilic surfaces interacting with each other, and ultimately the segregation of the hydrophobic surface from the water environment is what gives rise to protein structure and other structures as well, as we'll see in the next slide. For example, hydrophobic effect driving the formation of bilayers. Let's remind ourselves, this is a glycerophospholipid. There's that glycerol backbone in blue. We have through these two ester linkages, acyl chains, and then we have a polar head group here. Now we typically will draw this as a sort of a cartoon with a nonpolar tail and a polar head group. That segregation of polar and nonpolar is what leads to the formation of structure. For example, bilayer formation here, but more simple structures might be a micelle here, where we're exposing all of that polar surface area to water and burying in the interior. Imagine this is a slice through a spherical micelle and burying in the interior the nonpolar surface area. Now we probably won't have a void here, and in fact they might be interpenetrating more closely, but you get the idea. And we can also satisfy those interactions in a similar fashion by forming a planar bilayer, or we can roll this up into this vesicle. All right, let's look at a protein. Here is a cartoon of a particular protein. It doesn't actually even matter what the protein is. What I've done is color in red polar surfaces, polar amino acids, and in blue nonpolar amino acids. And what we see in general is that for a folded protein, the surface of the molecule is covered with polar amino acids. But when we slice through the molecule, as I've just done, we see that there's blue nonpolar residues packing into the interior of the protein. Now there might be some violations here and there, but by and large you see, even for a protein that's as small as this one, that the general rule is sequestration of hydrophobic surface area, exposure of hydrophilic surface area. That is the driving force behind protein structure formation. Here's a static image of that. Again, we take the protein, we see that it's covered with polar surface area exposed to water. We slice the molecule in half, we see that there's a hydrophobic core. And again, the sequestration of that hydrophobic structure is what drives the structure formation in proteins, as well as other biological molecules. That brings us to the end of this video. We'll spend the next video, 1.6, on discussing pH and ionization. See you there.